Today I'll be talking about fingerprinting electronic control units for vehicle intrusion detection. I'm Kyong-Tak Cho, and this is work done with my advisor Kang, Shin from the University of Michigan. As many of you may know, vehicles were composed of mechanical parts, but now they are being replaced with electronic parts, and also equipped with wireless connectivities. Although these provide controllability, efficiency, they are actually providing remote access points for attackers to actually compromise the in-vehicle network and then take control, which obviously is a security risk, as everyone knows. There have been a lot of attacks that have been demonstrated out there. So the question would be, why are these attacks actually happening? And what is difficult to actually defend against these attacks? So in CAN, which is the de facto standard for in-vehicle networks, ECUs, which are basically components of your cars, which actually controls your car, broadcast messages on the bus. Those messages contain information about the wheel speed, steering wheel angle, and so forth. And if we look closely at those messages are actually addressed based on what they actually contain, not actually based on the transmitter or the receiver. And each message ID is actually assigned to a certain ECU to be transmitted on the bus. So what this tells us is that we don't have any information on who actually is sending that message. So to discuss about vehicle cyber attacks, we consider two different attackers. First, a strong attacker who is taking control, that's the full control of a compromised ECU, so it can start and use transmission from the compromised node, and also stop transmission that it was usually transmitting. Another attacker is a weak attacker that only has partial control, so it can only stop transmissions. The existence of these two different attackers were actually shown in a different paper. For the attack itself, we categorize those attacks into three different attack models. First, fabrication. Second, suspension. And lastly, masquerade. I'll first talk about the first two attacks that can be made on in-vehicle networks. Normally, ECUs broadcast messages periodically. However, if an attacker takes control of an ECU and broadcasts the messages on the bus, and if that message has an ID equivalent to the one that another legitimate node is sending, and the send frequency is really high, it would override other messages and be able to control the vehicle maneuver. So this is why attacks have been possible on in-vehicle networks. So one representative example would be the one demonstrated in 2010 Oakland by researchers from University of Washington and University of California, San Diego. Although we didn't really illustrate suspension attack here, suspension attack is the one that instead of injecting messages, you can just basically just stop transmission and then no further deliver information to others. Actually, the attacker can be a little bit smarter than the fabrication and suspension attack. So we call that masquerade attack. Say we have two ECUs here compromised as strong and weak. With a weak attacker, the attacker can just basically keep sending its original message, but after some time passes, it can switch that transmission to a strong attacker and then inject its attack message instead. So why would the attacker actually mount such a masquerade attack? Well, first, if you look at the picture in the below, you can see that the ID is pretty much the same. So even though the attacker has actually mounted and injected the attack message, the network traffic actually looks pretty much the same. And again, in the famous GPAC, actually they discuss in their white paper, they actually had to shut down this legitimate node that was sending the original message and use another node to inject and control the braking behavior. So I would say that a similar attack to this masquerade attack was actually used for this Jeep attack. So the main problem in actually defending or detecting these attacks would be, first, we don't have any idea on who actually sent the messages on the bus. And also, even though we have actually detected those messages, we have no idea on who actually attacked. If we knew, we can actually respond to this attack pretty much quickly, and then patch, and then move on. So to answer to these two questions that I had before, in this paper, we propose a scheme that can fingerprint ECUs for intrusion detection. The fingerprinting is done by extracting clock skews of transmitters. So by using these clock skews as a reference, we detect malicious messages that are injected on the bus and detect intrusions. So what exactly is clock skew? Due to hardware imperfection, each clock runs at different speed. So if we have the rightmost clock as the true clock, after an hour passes, before it was set at 3 p.m., now one clock can show 3:59, another can show 4:01. So in such a case, we define clock offset as the absolute, as a difference in the reported times of each clock compared to the true clock. And we define clock skew as the differences in the rates in which each clock progresses. So in this case, over an hour, there was an offset of -1 and +1. So we would have a clock skew of -1/60 and +1/60. So in cars, actually ECUs have their own quartz crystal clocks, and they use them to actually schedule their transmissions and so forth. Well, because of hardware imperfection, they would have different speeds, slightly different speeds. And it was actually reported that you can have a 2.4-second clock offset over a day period. So this kind of justifies that clock skew might be a good candidate in fingerprinting the ECUs. Well, using clock skews as fingerprints is not really a new thing, because in the internet domain, it was previously used for fingerprinting the nodes. However, we cannot really directly transfer that idea to the automotive domain, because in the internet domain, most ideas on fingerprinting using clock skews require timestamps from transmitters and receivers, which are not quite available in vehicles. Even though we try to add them in messages, it would actually incur overhead, and it would affect the real-time communication. So in this paper, we did it in a slightly different way. We exploited the fact that most messages are periodic, and we use those periodicities to actually extract the clock skew values. So how? Say we have two nodes here. ECU A is intended to send a message every t milliseconds to R. Of course, it's a broadcast bus still. So ideally, from the perspective of R, it should have been sent at time t, 2t, 3t, and so forth. However, due to the difference in how fast the clock runs, it would actually have the slight offsets to its ideal timing. So accordingly, the received time would also include those information on the transmitter's offset. So if you look at the equations here, you can see that, in fact, if you look at the receiver's timestamps, you can see that the transmitter's clock information is actually hidden in those timestamps. So the next question was, how can we extract those offset values from the timestamps that we have? Because we have the measured timestamps, what we did was based on historical data and based on the log data and derived periodicities, we can extrapolate those values and make up an estimated estimated time that those packets would arrive. By taking the difference, we can have a rough estimation on what the transmitter offset will be. Of course, by just looking at just one of those values would not be enough, because there would be some noise in it. So we take an average and then obtain the average clock offset. But this average clock offset is an offset that has incurred for just those messages, not the ones that have been incurred for the previous ones and those. So what we do is we accumulate them, and if we accumulate them, what we get is something like this. Because ECUs have different clocks and different speed in how their clock runs, their slope, which is the clock skew in this graph, will be different. So if we actually monitor each message and draw a graph, If they were sent by different transmitters, they would have different slopes. However, if two messages were sent by the same transmitter, then we would exactly have the same linear model. You'll later see in the evaluation result that such kind of trend shows. So we learned this linear model continuously using an algorithm called recursive least square. Because clock skew is a hardware thing that is supposed to be constant, if we formulate this as a linear parameter identification problem, then we would have a constant, almost a constant slope value, and also the identification error of this recursive least square RLS being skewed towards 0. So with this linear model, what we did was we detected intrusion in two different ways. So per message detection and message pairwise detection. Per message detection is a detection that it just looks at a per message basis. So we just look at one message and then extract this clock behavior and use that as a reference for detecting malicious messages. So for example, what if an attacker actually injects a message using the fabrication attack that I described before? What would happen is, because the original legitimate node is sending the message anyway, it would actually change the outputs that we have in our system, because it outputs a measured timestamp that is very different from what we actually estimate. That would actually make our average clock offset increase. So in our linear model that we had, what would show is with an attack, it's as linear as normal, but with the attack, suddenly there will be a high shift in how this linear model changes. So this is very different from what we had before, because I said in the RLS, because it's linear, the identification error is supposed to be 0, whereas if an attack is mounted, suddenly there's a high value. Similarly, when a masquerade attack is mounted, because the transmitter of that message has changed from one node to another, the slope suddenly changes. So in this case, similarly from the previous attack, again, there's a high error in the recursive least square errors. So we detect such abnormal shifts using a cumulative sum analysis. So we do not really go into the details here. So if interested, you can refer to the paper. So instead of just looking at one message, we also looked at how the clock behaviors extracted from each message are related. I think this is one of the interesting observations that we had while we were reading off the CAN bus in the cars. So actually, when messages were sent from different ECUs, obviously, as expected, the offsets were uncorrelated. However, when they were sent by the same ECU, we found out the instantaneous offsets were actually correlated between them. So what advantage does this provide to us? So per message detection was kind of looking at the long trend on how this linear model would change, on whether the slope would change, and whether there's a high deviation from it. On the other hand, message pairwise detection is actually looking at its instantaneous values and looking at their correlation. Because it's looking at their instantaneous values, unless the attacker is kind of changing the temperature or the instantaneous workload in real time and in a very fine-grained manner, it's very difficult to imitate this. So this is the result that we had when we read the CAN bus traffic from our car, 2013 Honda Accord. So you can see on the left-hand side, once it was verified that it was sent by the same transmitter, it also showed that the clock offsets were actually correlated. So we can use this, again, as a similar linear model to take as a reference and then detect the intrusions as well. Also, if it was sent by a different transmitter, the correlation showed a value near 0. Similarly, when we used the data that was logged on a 2010 Toyota Camry, the result showed the same. So if it was sent by the same transmitter, it showed correlation, whereas if not, then the correlation was 0. So to evaluate our proposed IDS system and also our fingerprinting scheme, first, we did that in 3 settings. First, we configured a CAN bus prototype. This node is actually composed of a CAN shield and Arduino Uno is just $50. So we compose them as a CAN bus prototype as being connected to each other through a 2-wired bus. And using those nodes, we actually logged off data from a 2013 Honda Accord, which was my car, actually. But using my node, you can connect to the OBD2 port and then just read off the data from the CAN bus. So what you can do is you can also not only read, but you can also inject messages to the bus. So in this setting, all these 3 nodes were actually reading all the data that was actually on the bus, but also we were able to program them to inject and just control things. And lastly, we also used CAN log data to verify our fingerprinting scheme. So the data that we used were data that was logged by researchers from University of Tulsa on a 2010 Toyota Camry and a 2010 Dodge Ram pickup during a 30-minute drive. So this is what the fingerprints actually looked like on different cars and different settings. So you can see that the models that we actually constructed based on message periodicities were actually all linear as expected. And more interestingly, that if those messages were sent by the same transmitter, they had the exact same slope. And also for those, they had correlated offsets that I have shown before. Again, also to kind of evaluate how our IDS system would react to attacks that have been made on the CAN bus, we programmed one of our nodes as the IDS system that we proposed, which is the clock-based IDS, and another as an attacker that can inject messages using fabrication attack or masquerade attack. So this is the result that we had on our IDS system. So as shown as an example before, because of the fabrication attack, there was a sudden shift in how the linear model changed. So the blue dot line shows what was expected, whereas this red line shows what was actually output on the system. So our system was actually showing that sudden shift in that linear model, so we were able to detect that attack. And more importantly, we evaluated how our system would react to this masquerade attack. This masquerade attack is an interesting attack because even though it's mounting the attack, the distribution of message intervals doesn't really change. So that means for existing IDSs, for just look at message periodicity, would not really be able to capture this attack. So as you can see on the left-hand side, the distributions before and after the attack was pretty much the same. However, our system was looking at attacks in a different angle. We were also looking at whether the clock skew value was changing or whether the correlation was changing also. So here you can see that there's a sudden jump in the errors that we were detecting. So our system was alerting that there was a masquerade attack that was mounted on the bus. And the last thing is, I think, another very interesting aspect that we had. So once the attacker actually mounted this masquerade attack, that's the red line, you can see that the slope suddenly changes. But that slope changed to a value of a message that was also sent by the attacker. So what does that tell? We can tell that by looking at the clock skew value, if the attack is done periodically, then we can say, oh, okay, this attacker must have been using this ECU to inject this message. So now we have a rough idea on who actually was attacking the bus. Also, we evaluated our message pairwise detection, which looks at the correlation between messages offsets. So people can ask, what if the impersonating node has near equivalent clock skew in the first place because of the birthday paradox? Or what if the attacker tries to control match its clock skew by heating up or cooling down the ECU? So we kind of evaluated a similar scenario by having this attack still with the same clock skew, but of course with different instantaneous offset, because we consider that to be difficult to imitate due to the requirements of matching the workloads and instantaneous temperature. So even in this case, because we were looking at the correlations between the offsets also, it was shown that our system also detected that masquerade, that is, the switching from one transmitter to another. False alarm rates would also be definitely an important aspect for IDS systems. So this shows an RC curve of our system with just per message detection. We were able to detect all 900 attacks that we mounted using fabrication and suspension, but not all masquerade, because if the attacker switches from one to another in a very good, with a very good timing, then because only this clock, and that clock skew is pretty much the same before and after, then we won't be able to detect that with just per message. But if we added message pairwise, which looks at instantaneous offsets and their correlation, we were able to actually suppress all those false alarms and detect all of them correctly. So to conclude this talk, I have talked about a clock-based IDS, which detects malicious messages looking at their timings. So basically, the idea was to fingerprint transmitters by extracting clock skews of them. And one merit of this IDS system overcomes some limitations that existing IDSs had for vehicles. And most importantly, we didn't require any change in the protocol or message itself. So we believe this is one good merit for this kind of approach. So although our talk was more focused on intrusion detection and a bit on root cause analysis, we believe these kind of schemes can be applied for authentication schemes and all other schemes that you can imagine. Thank you.
Jae-Han Jung, Microsoft Research, great work. Next, my question about kind of timeliness of your detection. Oh. I assume that if attack's going on, ideally you want to detect like right away, right? But it looks like your scheme, you need to kind of observe a little bit of messages to be able to detect this clock skew. So can you tell us a little bit about the timeliness of your detection?
Oh. I think that's a great question. Because as you said, to detect, say, fabrication attack, we can detect that immediately. But for masquerade attack, we have to get that clock skew value, which takes some messages to actually measure that. So in our experiment, we took 10 messages to get one clock skew, say, clock offset value. So that would take around 100 milliseconds for a 10 millisecond message. And so, yeah, it depends on what messages we are trying to do. And that's one aspect that we should look into as a future work. So the timeliness is another important aspect.
Hi. So the clock skew is typically affected a lot by environmental factors like temperature, right? Yeah. So in your experiments, have you also looked whether your detection accuracy is affected, for example, when, let's say, engine heats up, whether this creates additional false positives? And second part of my question, I mean, the communication on the CAN bus is not strictly periodic, right? You have event-based messages that may also influence the periodicity of your communication. So how have you taken this into account?
Can you repeat the second, sir?
The second question is there's also event-based communication on the CAN bus that basically violates the periodicity of the communication. So have you seen this, and has this led to false positives?
Okay. So to answer to the first question, we did. In our car experiment, we didn't really actually try to heat it up or cool it down. But for heating up, it would incur false positive results if it's changing too much. But what we also looked at, as you can see, we also looked at the instantaneous values, how it changed. So that changes are less impacted by the temperature itself. So that's why we try to combine both. So for those temperature effects, we consider message pairwise detection to actually be able to deal with that. And to answer to the second question, it depends on the car that we have. So for the car that we have for the Honda Accord, most, say, 95% were periodic. And for the Dodge Ram pickup data that I used, all 51 messages were periodic. So in cars, I saw, except for 2 or 3 messages on the CAN bus, everything was periodic. So we're not really focusing on the aperiodic ones, but we're just focusing on the periodic message.
Okay. Did you also looked at the car in operation, so while driving, while triggering actuators, or was it basically just the baseline when the car was, the engine was running but not driving?
So I think messages are mostly configured to be periodic regardless of how they are actuated. For some messages, of course, they can be aperiodic. So as you said, as a baseline, we have everything as periodic, so that's what we use.
So, Kyong-Tak from Quest, if the ECU is compromised, can it learn the clock skews and try to emulate exactly other ECUs' behavior?
Yeah, exactly. So what the attacker might do is try to learn the clock skew, heat it up or cool it down, and match the temperature and try to match the clock skew. But what we observed is even though it matches that slope, the instantaneous change cannot be matched unless you control your temperature in fine grain, and also that clock skew would also be affected by other factors. So unless it is sent by the same ECU, that instantaneous value was not quite matchable. But it could be possible. I won't say no, but I would say it's very difficult compared to just like matching the long trends. Yeah.
All right.
Sahar Mazloum from George Mason University. Congrats for the nice work. I would like to know, does these, for example, fingerprints or these clock skews are affected by the time or wearing off, or do they change by the time, or if somebody reprogram or exchange these ECUs with the new ones, the clock skew is different or they're the same?
So
how long they are valid, basically? How long these fingerprints are valid?
Are valid?
Yes.
So for our experiment, we actually logged the data for at least an hour. So for an hour, we will say yes, but for like 24 hours or so, I didn't really experiment up until up to that time, so I'm not sure. But this RLS algorithm, why we used it is because it's recursively learning the slope, and unless that slope is suddenly changing, as in the fabrication or masquerade attack, it would actually adapt to how that is changing. So that can also be considered as false positive results that might have to be considered in this system. Yes.
I'm just curious about to know, does these fingerprints are different in the critical ECUs compared to the non-critical ECUs, or there's no difference?
For fingerprinting, we know which message was sent by which ECU, but we don't know whether that ECU was safety critical or not. We just have a rough idea based on just looking at the periodicities, and if the frequency was very high, then we just think it might be a safety critical ECU, but it was not that.
Thank you.
One last question.
Hi, Dongguan Kim from KAIST. So can you apply this technique to prevent the canned message injections?
Oh, yeah,
because if you can even though you can detect the canned messages, then after the accident, it's not right.
So yeah, that's one great question. So this is not really for prevention, it's for detection. But for masquerade attack, as I said, even though the attacker actually switched and doesn't really inject something malicious, the network traffic would look fine, the driving would be fine, but the switch in the transmitter would be detectable. So we can somehow think that as something preventing a further, say, fabrication attack or something, but we cannot really prevent everything. We're just trying to focus on how to detect it. So I believe prevention should be done in a slightly different way.
Or maybe you can optimize the techniques to check the canned messages before processing the canned messages in each ECU. Then maybe
yeah, well, that can be another way.
Thanks.